And great. And I think we can start to show and people will join us as time goes on. Welcome everyone to our April VAST seminar. We're delighted to have two speakers today who are going to talk to us about lightkurve packages, as well as some of their experience developing them. Before we move to those, just a few announcements. Next month, we're having a joint session with the SciCodes group. And we're going to hear about the software development process, things like citations, software publishing, and so forth. Alice is going to be lining up a great lineup of speakers for us. And so everyone, please come back for that and hear more about software infrastructure. In June, our proposal is to have talks from graduate students who might have been doing projects writing code in this past semester or past academic year. Catherine is going to be organizing that, and we're going to do it in the format of lightning talks. And so if you are a grad, or if you know a grad who has some cool project that wants to spend 5 minutes talking about it, have them propose a talk on our GitHub page. We'll post the link in a little bit. And finally, in July, we're going to focus on teaching computation to students, again, in the format of lightning talks. And we're going to gather up a bunch of people who have experience doing this and talking about what works, what doesn't work, sharing resources, and so forth. I'll be organizing that. And likewise, if you know someone or if you have some experience and want to share, propose on our GitHub. And we'll do some work in preparing for all these over the next month. All right, with that, we're happy to move on to our speakers today. We're going to start with Rebekah Hounsell. Rebekah is at NASA Goddard Space Flight Center and University of Maryland, Baltimore College, or Baltimore County.
Baltimore County.
County, okay. And she's going to tell us about her lightkurve package and its applications to astronomical observation. So, Rebekah, you can go ahead and share. Looks great.
Just need to unmute myself and then I'll go ahead and play. And just to clarify, it's not my lightkurve package. It is something that we over at the TESS and General Investigator Office use, but I will explain more of that in my talk. Okay, so can everyone see my screen okay?
Yep, looks great.
Wonderful.
Yes.
Thank you again. So thank you so much for having me here today. Yep, my name is Rebekah Hounsell. I am a support scientist in the Transiting Exoplanet Survey Satellite General Investigator Office over at NASA Goddard. And I'm here today to talk to you about our main workhorse. It's a Python package that we use a lot to analyze our data, which is called lightkurve. And here just put down that it's a friendly Python package for making discoveries with Kepler and TESS data. So, what was the original purpose of lightkurve? Well, this was lightkurve was originally developed to help with exoplanet discovery and finding certain signals within data from the Kepler mission, which ran up until 2018, and then with the TESS mission, which ran from 2018 until, well, it's still going now. We're actually have entered the 5th year. So it was actually TESS's 5th birthday yesterday, I believe. So yay for TESS. And so lightkurve was really developed to help the user take the data from these facilities and analyze it to find exoplanets and make those discoveries. Now, just a quick demonstration here of the TESS, how we are able to detect exoplanets. So we use something called the transit method. So essentially, as you see here, when a planet passes in front of its host star, we have this dip in the light output, as you see in the plot down here. And then this dip is actually relative to the size of the host star versus the planet. So from that dip, we can kind of determine lots of important information. So TESS looks for this signal as it observes almost the entire night sky. And that's the data then gets collected, and then the user community looks at it and finds these transit signals. So just a brief discussion here about the code functionality. Lightkurve itself is completely open source and community driven. There's lots of documentation and resources, which I have put here. So there is just wonder if I click on this, whether it will show up or not. Oh, it did not, and it just undid my talk. Okay. So yes, Lightkurve, we have an API and documentation as shown here. It is all publicly available. It's all up on GitHub, so you can go and investigate for yourselves. It is pip installable, so very easy to install. If you don't want to install Lightkurve, so you don't want to have it, or you don't want to have other packages on your computer, you can actually access it easily via Google Colab or notebooks, or via Tyke. So Tyke is a service that's up on Mast, and you can actually just create an account there. You don't need to install anything, and just simply run your code and look at your data through those services. The requirements for this are very common Python packages for numerical computing, plotting, and astronomy in general. And additionally, one thing that I love about Lightkurve is because it's on GitHub, and the way that we work with the community is you can suggest updates and modifications. You can tell us if there are issues, and just showing briefly in the next slide. So this is just a little video I took off the GitHub, just showing, you know, discussion about the package, the documentation, how you can easily get started with it, and how you can contribute. There are many pull requests, so people essentially post lots of issues, and then we address each one, and then different pull requests get made. And then there's been a lot of activity, even just over the past month or so, of like, you know, different issues that the community has reported. And then the General Investigator Office, which has now taken over the running of Lightkurve, trying to respond and working with the community to fix and adjust those issues. So it really is very much a community package where, you know, if you have problems, if you have concerns, if you have ideas, you can post about them, and, you know, we can work with you on those issues and fix them and make different pull requests. Okay, so talking about just some examples of what Lightkurve does, its functionality. Well, let's go back to talking about the science. So L9859b, this is a terrestrial exoplanet that orbits an M-type star. Its mass is 0.3 Earths, and it takes 2.3 days to complete one orbit around its host star. And so just for an example, what I'm going to do is talk through how one might obtain information about this using Lightkurve, and then reduce that data to put out the transit signal that was discussed earlier. So searching for the data. So I hope everyone can see this, my screen here. Searching through the data. So TESS has, so Lightkurve has a variety of ways in which to search for the different data products. So I'm just going to pause here for a second. So we have full-framed images. So these are a set of full all-science collateral pixels across the sky. So TESS operates by viewing sectors of the sky in these 24 by 96 degree fields. And it looks at that region of the sky for about 27 days, and then it moves on to the next one. So a full-framed image is a set of all science and collateral pixels across all CCDs of a given camera. There are 4 cameras. And they used to have a cadence of about 30 minutes in years 1 and 2, and then 10 minutes in years 3 and 4, and 200 seconds in year 5 onwards. So you can see the different, if you look here, the different times, exposure times. So you can kind of search for these. If I'm going to go back on this one, by using these different functions. So we have TESS search cut, and that, which will basically show you whether your object is in a given full-framed image. And I'm just going to show you the result table of that search function. And it gives you in the table this link to another database which tells you how to use TESScut. So that would be like how to cut out a little region around your object of interest from a full-framed image. The other data products are target pixel files. So these are postage stamp files focused on select targets of interest. And each stamp has a cadence of 2 minutes or 20 seconds. And this is what I'm showing here, where these data are reduced by the spot pipeline. So they have further data reduction applied to them, like removal of noise and things like that, so the user can get a better grip on the data faster. And then we have Lightkurve products. So these are the light curves that are produced from the target pixel files for your objects of interest. Again, we have the SPOC one, which is the typical science one, but there are also other higher level science products here, which if you click on each link, as I'm showing you in the table, takes you to a different page, and that explains what the higher level science product is. And again, I'm clicking here on the quick look products, and that takes you and shows you a discussion about what a quick look product is. And so what I'm saying is that the Lightkurve functionality when you search for these objects. Gives you a lot of information in that table just as is. So this again showing me Eleanor. But if I take you back to the beginning, hopefully if I can do that here. Yeah, one of these. Yeah, so whether you're searching for the full framed image information, the target pixel file, or the light curve, this table typically gives you, which sector they're observed in. This is a sector. It gives you the year that that data was collected, and then I said these hyperlinks to give you more information, and then the exposure times, and then your object. Okay, so you can search for that data, but how do you go about downloading it? Well, it's pretty simple, essentially. I've noticed that there seems to be a delay in my video here. Is everyone seeing that? I'm just looking at it. I don't know. Do you see the downloading data page?
I do.
Okay, great. Sorry. In my video, it seems to be having a delay. So I'm glad that you see the downloading data page. Wonderful. Thank you. Okay. So if you want to download your data, how do you go about doing that? So it's pretty simple. You just pick which element of the array you wanted beforehand, download, and then you can specify different quality bit masks. So that is basically just identifies the quality flag that should be used to mask out bad cadences or not. Typically you have default, or you can have hard, or you can have soft, and then you might get some more data that isn't has been affected by other things. I typically use default or hard just because I don't want my data to be affected by various systematics that I'll be talking about later. So I'm just going to show you a quick movie of doing that here. So you can download, in this instance, I'm downloading a target pixel file, so a little cutout around a region. And you can actually have different ways of plotting this information to see what it looks like. So you have the pixel number versus the flux. There's also a nice fun little thing called interact here. And this shows you essentially, it shows you the aperture, so these are the pixels that are selected here. And it also shows you the light curve that's created as part of the aperture. And you can move across this bar here to see how things change with time. So you can see in your image here that you can also manipulate the contrast essentially. But yes, you can also watch it with time, and you can adjust the pixels that make up your aperture as well. So you can reselect if you want there, and then you can also save that light curve, and you can save the aperture as well. So this kind of offers a very nice way to interact with data, and also gives you information about the surrounding region. Another way to get information about the surrounding region is to use this function called interact sky. So if you have a look here, this shows you your object of interest, and it also shows you the surrounding region around it. So I'm just adjusting the contrast, as you can see here. And then if you can see all these red dots, and if you click on those, that gives you information. So that can give you the test magnitude, also gives you some Gaia information, RA and DEC, and you can do that with any one of the red dots here to see what is kind of in your surrounding region, which can be quite useful if you're trying to understand, potentially contamination or, anything else that's going on in that region as well. So I particularly like these kind of interactive functions that a user might use. Okay, so that was looking at a target pixel file, but you can also download the specific light curve data itself that's been produced by the science operations centers. And so this is just showing you a quick video of that. So that's essentially, you downloading your light curves before, and this provides you with a table of information. So your time versus your flux and your cadence, and a lot of other useful information. Now, in the light curve files, there are two kinds of flux. There is the simple aperture photometry. So this is the light curve is calculated by summing together the brightness of the pixels that fall within the aperture set by TESS. You saw that before when I was selecting the pixels. And then there's the pre-search data conditioning SAP flux. And this is flux from which long-term trends have been removed using co-trending basis vectors. And this is usually cleaner. And this is the information that gets produced by the Science Operations Center. And so what I'm showing you here is just some of the information that you can find within a light curve file. So you can plot things like the time and the flux. They're typically stored as you would expect with AstroPy. And then you can plot this up. So we have the time, the date, time and date shown here. And then you can plot the SAP flux versus the PDC SAP flux as well. So you can just get an illustration of how they look compared to each other, and therefore try and get an understanding of how you might need to process your data if you only have the SAP flux. But yes, there's lots of different ways that you can interact with your light curve data as well. And I'm going to give a few examples of how you might manipulate and interact with your lightkurve data using lightkurve with a K, the lightkurve software. So this is just showing, you know, a couple of different functions here. We have the flatten, so you can remove long-term trends using this flatten function. You can fold the light curve, and this is really useful if you want to fold the light curve on the period of the planet potentially and help to recover that transit signal, which you can see here. And then you might want to also bin your data, especially, you know, if we're using 200-second cadence data or 2-minute or 20-second cadence data, binning can be very useful to pull out some of those signals, as I'm going to be showing here. So this is then recovering the transit from the planet. And this example was just shown on the PDC flux. You could do it on the SAP as well, but then be aware of other systematics that might be shown. Okay, so there's another function which is very useful in lightkurve, which is creating periodograms. So in this example, I look at KIC 10244202, an eclipsing binary that was detected by Kepler. And 2periodogram literally just creates this periodogram from the lightkurve object data. And within that, you can again search the API of lightkurve, and it gives you all the options for, you know, the methods by which you want to do this. So I'm just going to go through this video here, just showing this. So this is the scattered data that is recovered from the lightkurve. This is the PDC SAP flux. And this is just showing if you wanted to normalize the data and then apply the periodogram and then plot it. So I believe still under, yeah. So this is putting it and showing the frequency power function. And then if you want to adjust that and make that log scale, that's also an easy option. And then you can obviously look at the properties of that periodogram. So you create a periodogram object, and then you can look at the properties of that to derive certain things. So such as, you know, the frequency at max power, which is 1.9 days, the period at max power, all those sorts of things. And this can be really useful in trying to, you know, get the period of the system. And again, you can use the period that you derive to fold your light curve to show that. Now that doesn't look great, so you might want to manipulate that and play around with that a bit, as shown here. So this is a very quick run through of how, you know, the period function works in lightkurve. Additionally, we have a function which you can look at to obtain the average frequency spacing and the frequency of maximum oscillation for solar-like oscillators as well. So this is just a very quick rundown, and there are actually on lightkurve there are tutorials which run through each of these examples of using the periodogram and using the seismology function here as well. So these metrics, what I'm talking about here, can be used to estimate the mass and radius and surface gravity of a star. And there's various functions that are inbuilt in lightkurve to help you do that when you obtain your data. So it's essentially, you know, you create a periodogram, you create a smooth version of the power spectrum, you remove the background noise from the periodogram object, and then you essentially run through and use these things called two-seismology to help you to diagnose and obtain things like the frequency spacing and the frequency of maximum oscillation amplitude. We're just running through here. So it's pretty easy to recover these values from your data. Obviously, you need to dig around into the API, the documentation more for setting up specific parameters and the best case for your object of interest. But it's pretty easy to derive these things. And then again, you can go on to obtain, okay, different power spectrums, etc. I'm just giving you a breakdown of this very quickly. And so yes, you can use these parameters to then calculate the following, such as stellar mass, stellar radius, and surface gravity. And there's all these sorts of diagnose methods as well to help you get a better understanding of what your data is doing to make sure that, you know, what you're pulling out is correct. So this is one of the diagnose methods that's being shown here. And then finally, estimating your stellar parameters. So beforehand, I mentioned that there were different kinds of flux that could be obtained from your light curves and your target pixel files, the PDC SAP and the SAP flux. And what I'm going to go over now is just how, if you do not have a light curve or a target pixel file that has been processed more by the SPOC, how you would try to remove those systematics yourselves using some of the inbuilt functions of light curve. So I'm going to start this with a K2199 and just talk about this. So there's actually, again, all these tutorials exist online within the light curve, on the light curve page. And I'm just going to give you an example of how you can use the pixel level decorrelation function in lightkurve to do this. So as I said, TESS has instrumental systematic trends, which can make detection of various signals very difficult. In lightkurve, there exist various methods to remove these. So co-trending basis vectors, regression correctors, pixel level decorrelation, or self-flat fielding. And I'm just going to show this video here, which is using this object I discussed earlier and showing you what the target pixel file looks like. And then essentially just importing from the light curve corrector class, this PLD corrector. So PLD is a method used to remove systematic trends introduced by small spacecraft motions during observation, and it identifies the set of trends in the surrounding pixels of the target star, and then performs this linear regression to create a combination of these trends, and then we use it to remove the noise. And so this is essentially just going through, calling that corrector and applying it to the data, and you can see how the data looked previously in the red, and then once it's been corrected, as shown in the black here. And then it just shows you the dramatic effect in the uncertainties. And then again, there was this diagnose function, so you can see the uncorrected data, the corrected data, and then what exactly was modified and done to correct that data, and then any outliers that you might see as well. Okay, so this is just my final remark here. So TESS, even though it was originally designed to find and detect exoplanets through the transit method, because it essentially observes almost entire night sky. I think by the end of the second extension, it has now observed 93% of the sky, and some areas several times. It really is an amazing facility for looking at all sorts of things, not just exoplanets, like stellar variables, explosive transients, solar system objects as well. And so while as a community that uses TESS is growing and using it in different ways, we're developing new techniques or thinking of new ways in which light curve needs to be adjusted, or new ways to show the community how to use TESS data on things that it was not originally designed for. And so that's really comes in with having this GitHub page where people can report issues or problems, and that we as a community can work together to getting the best data from TESS. And with that, I'd like to thank you for your time.
Fantastic. First off, these are very nice slides.
Great, I'm glad you liked them.
I mean, I was like really impressed, but it's also an impressive amount of work in developing this package.
They have been working on it for a long time, yes.
Yeah, we have some virtual applauses if you look in the participants. We have time for a question, and otherwise we're going to move on, and then we'll take all the common questions at the end. If anybody has a quick question, you can unmute or raise your hand.
Rebekah, have you seen any novae go off?
Yes. So the amazing thing of TESS is because it is a stand and stare operation, if a nova happens to go off in that region, and it's bright enough to be detected by TESS. So typically TESS can get down to 21st magnitude if it's not too in a crowded region, but typically needs to be a bit brighter than that. But yes, there are novae that have been observed in TESS data, and then, like I said, the nice thing about it is if it goes off, then you can get actually the nice rise and the pre-maximum halt as well. So TESS is amazing for getting that really early data and at a very high cadence as well. The cadence now, as I said, in the second extension with the full framed images, which is what typically you'd have, you can't select objects of interest if you don't know about them yet. Typically would be 200 seconds now. So yes, you can get beautiful light curves of novae from TESS.
Okay, I'll continue this offline.
Wonderful.
Awesome. And we'll have time for more questions towards the end, but we're going to move on to our next talk. Let's see. I have to do after 3 years, I still have to check to see if I'm unmuted on Zoom. I'm still paranoid about this. We're going to hear from Konstantin Malanchev, who is going to tell us about light-kurve, but also about his experience using Rust for developing Astro programs. So let's give our attention to Konstantin.
Hello, everyone. Thank you, Rebekah, for very beautiful talk and for great package, which most of us probably enjoying use. And if somebody is not enjoying, they just haven't used Kepler or TESS data yet, I think. And hello, everyone. I'm Konstantin Malanchev. I'm postdoc at University of Illinois Urbana, Champaign. Moving this summer to Pittsburgh to join Link Frameworks project as a research scientist at SAMU, and I would like to present you my experience on developing lightkurve. Sorry, very lazy naming, I know. lightkurve packages for Rust and Python for time series analysis, basically for lightkurve feature extraction. Okay, so I will try to spend more time talking about Rust itself because I think my package is quite niche and quite straightforward, doing straightforward things, very simple and straightforward tasks, but very fast. And the community would be more interested in listening about Rust and how we could use and should we use it in astronomy. So let me start with this simple question. Why go in Rust? So Rust is quite a modern language. It started something like 10 years ago, a bit more probably, in Mozilla as an experimental project to develop a new compilable language, which would be memory safe, fast, and convenient for different types of problems, but mostly for quite low-level coding. And of course, first of all, it was used for Firefox, and then it was released in public, reached version 1, and now it is stable language development, which is really, very high velocity of development of ecosystem, compiler, and language itself. So the first aims of Rust are to be fast, parallelizable, and safe. And by safe, it is, quite safety is a big topic. And in Rust, when people say safe, they usually mean memory safe. So no undefined behavior, or almost no, and safe in terms of parallelization, safe in terms of access to the memory in multi-threading. So it has a compile time memory management model, so no garbage collector. It has resource initialization like in C++, so you could create a vector, for example, like here, and when you exit scope, your vector is automatically deallocated and the object is destroyed. So still, since it doesn't have garbage collector, it has no virtual machine or other runtime requirement, which is great for using it with other languages, with other technologies. You don't need to bring anything with you after you build your binary or your library. So another specific thing about Rust is ownership model, which makes it memory safe. You could think about it if you use C++, more or less modern. You could think about it as C++ move semantics. So almost everything is in Rust is moved, not copied by default. Only small and easy to copy objects, references, numbers, other small stuff could be copied. and you could create your own copyable types, but generally everything is moved. And since object is moved, you couldn't use it anymore, not because of, UB or some standards, but because a compiler wouldn't compile the code after you're trying to use moved value, like it shown here. And so we're creating a string, we move it to a function takes it, and this string is destroyed after the function evaluation. So we cannot use it. It's delegated, is destroyed. We cannot use it anymore here to print the string itself. So we could fix it in two ways. We could just not trying to use it after moving, or we can pass reference. So another specific thing, I wouldn't talk about it too much because it would take probably too much time, is lifetimes. It's another thing to make another part of this memory safety model. And this brief example showed these lifetime generics. You see this apostrophe A or quote A generic variable, which shows lifetime, which is kind of lifetime annotation, which actually probably will be appear in C++ in near future, in 27 or something. I'm already not following C++ word so good. And you could annotate your references to help a compiler to understand that output reference will not outlive any of input references here. So Rust is not object-oriented language, at least not in the same way as C++ or Java, for example, or Python. So it has encapsulation. You could think about it just like structures in C, but has no constructors and no polymorphism. So still, it has structures and it has associated methods, but it doesn't make it really object-oriented. So this new method is not kind of static method, is not really a constructor because it's finally just creating a structure, in a C-like way. But we have the syntax sugars, so we could use attributes and we could call methods. But instead, you could generally more or less do the same job as you do, for example, in C++ or Java with other tools Rust provides, namely generics, traits, enums, which are rich enums, and syntax level macros, in contrast to C++, textual level macros. So I don't have time to show all the things right now, but I really enjoy Rust enums, and this is a small example. So enum in Rust is not just, integer having some titles, having some names. It is algebraic type, so it's a union of several types, and you have very convenient match syntax to select a specific variant you have inside your enum. And so you see you could parse the data inside and use it, for example, to create string, return it, and print something in our main function. And Rust is designed to have easy interop with C using so-named unsafe code. So there is again a short example where we create C string and getting a pointer and call function from C standard library inside these unsafe blocks. So Rust memory safety requirements are too strict to design a real-life language with interop with other languages which do not have these restrictions, and to develop, for example, base line collections and other low-level data structures. So it has these unsafe regions where you could bypass some, not all, but some memory safety rules. And you should be very accurate using this unsafe code and test it to be memory safe yourself. So Rust is not really a magic tool which makes memory safe everything. And about Interop, it has really nice tools to generate, for example, generate libraries, libraries to call C functions just from C header files. So using LLVM, which is a engine of Rust compiler of Rust C. Okay, Rust has a really great ecosystem of tools. So the main tool you probably will use if you're starting building Rust will be Cargo. It is a package manager, build system, and much more unit test runner. So there is kind of built-in simple unit test framework into Rust. Rust has centralized package repository. You could think about it like PyPy for Python. Of course, you could use your private repositories if you want. And while you push your code to Crates.io, it automatically pushes to docs.rs, and documentation is being built from doc strings you have in your code. Very convenient. So since Rust uses LLVM, it can compile to many LLVM targets like WASM for running in browser, or even no OS binaries with no standard, no operation system standard library, with no Rust standard library, with no Lakita probably, but you could still run it on bare metal if you want. Rust has a great async frameworks for web development mainly, but also for other kinds of input-output like Tokyo. And Rust standard toolchain is really great and large and huge. So it includes compile itself, code formatter. Think about it like Black or in Python or Silang. I've forgotten its name. So Silang FMT or tools like this for C++. So it has a linter, which is called Clippy. It has a docs generator, so you could generate HTTP docs on your computer before posting them to docs.rs. It has language server for IDs. By the way, it has great support in C-Line, in JetBrains ID for C and C++. And it even has an experimental interpreter, which is used to finding undefined behavior in these unsafe blocks, if you have some. And it has other great tools like criterion for benchmarks, debugging tools, interrupt with other languages, including C++, which is quite limited, of course, because you couldn't connect all C++ features to Rust features, but it's still very convenient, and code coverage tools. Rust is already highly adopted by industry. So the greatest thing happening in open source, in very large open source projects. So I already told you that Mozilla initially developed it for Firefox. I believe that CSS engine in Firefox is now written in Rust, and it's already used in Chromium. I say Google Chrome, it's not open source, but I mean Chromium here. It's used in Android, and it is the second official language of Linux, which is great. So Rust toolchain is already in release kernel versions. There is still no real Rust code running in your with your Linux kernel, but there are few drivers. So Rust is aimed to use as a for drivers in Linux for now, and it is already used in development GPU drivers and drivers for SSD. So there are many cool tools written in Rust. So, for example, about Python world, it is rough linter, which is very fast and easy to use. It is Polar's data frame library. It is kind of pandas, but it's more about, it's going deeper into SQL-like processing of your data. So if you run the whole pipeline from reading your file to getting the final numbers from it and write it all in polars, it would run really fast. And they advertise that even after pandas version 2, polars is still the fastest way to read CSV file and create pandas data frame than pandas itself. So there are some cool, awesome projects using Rust. For example, our beloved Aladdin Light version 3, if I remember right, uses Rust. So you probably already use Rust right in your browser. And great adoption by large companies. So all these, largest companies like Microsoft, Google, Amazon, Facebook, Apple, they use Rust internally and sometimes for their open source projects. Okay, so what about Python? There are different attempts how you could use Rust with Python, but the most developed and probably greater thing to use it is with PyO3 create, which provides bidirectional interoperability. You could call Python from Rust, and you could create Python binary extensions using this create. Create is just name for packages in Rust world. So here an example where in Rust you just call CPython APIs, but translated to Rust. Yes, so we import something, getting attribute, sets some locals for our code, and running the code and getting the result back in Rust. Or there is a very cool inline Python create, which allows you just running Python code very convenient way from Rust, and even using Rust variables inside Python code.
So you have like 5 minutes.
Oh my God, it's terrible. Okay, thank you. I will speed up. Okay, so there is great interoperability with NumPy. I will skip it. Less great, but still good interoperability with Arrow. And there is great packaging facilities for Python binary extensions like Meteorine, and you could use it to build your wheels and publish them to PyPy. Okay, drawbacks very fast. So of course it is young language, young ecosystem, so it's not mature in many ways. It has really steep learning curve because you need to get this ownership thing to start to use it. So it's right now it's not so great for science because not a lot of science packages exist, and not a lot of bindings to science popular science packages exist, but some of them are there. For example, BLAS, GSL, FFTW, and so on. Okay, and I probably skip the rest here. I'm going to lightkurve because I have just a few minutes. Okay, so the motivation of the project is creating lightkurve feature extraction package for a regular time series. For light curves, we usually have when we use ground-based facilities, not great satellite facilities like Kepler or TESS. And there are many options which we could go through, but features are still fast, affordable, easy to deal with, and they work for very heterogeneous types of objects. Okay, I'll probably skip more or less the history. I'll go very fast through it. So we started with in a SNAD project, which is dedicated to light curve anomaly detection. We first started with light curve approximation for supernovae, but found that it is not scalable for scales of tens million light curves of, for example, ZTF date releases, or Gaia, or pan-stars, or future LSST. So we just moved to feature extraction. Okay, I'll skip probably this part. And initial version of feature extraction, very initial version 0 was written in Python, of course, but we found that it is really slow for many reasons. Interop with our database is slow, feature extraction is slow, everything is really slow, and we wrote it in Rust, and then created Python being links back to interrupt with. Okay, skip this slide as well, and this with results. So the package itself contains something like 30 different feature extractions for pretty simple features like, magnitude statistics like mean, median, momentum, and quartile based, shape-based statistics, and more sophisticated stuff like fast Lomskargel parallelogram, which utilizes FFTW or MKL on Intel, which makes it pretty fast, for example, faster than AstroPy implementation by factor of 6 or 10. And we have few parametric light curve feeds, so to feed light curves like this, like supernova or other transients, for which we also use some C or C++ libraries like Ceres or GSL, and some other features, so probably skip them for now. So, okay, this is small example of how you run it. It's quite straightforward. You create these feature extraction objects from Python classes, and then you extract features, and you have them for your single light curve or for many light curves. You could run it in parallel, utilizing multiprocessing written in Rust, so it doesn't affected by GIL in Python. So some benchmarks here, which are a comparison between Rust, which is Rust implementation, which is green, blue, which is our selves Python implementation, which we made for unit testing and for benchmarking. And feeds, it's quite popular feature extraction package written in Python. So you see that this green is much faster usually than all implementations in Python. And we also have pretty low interrupt cost. Oh, I have no time, I know. Okay, I'll almost finishing. Which is even lower than interrupt cost for NumPy functions. But we did it with a small trick. We do not support lists or other, array-like objects. We support only NumPy arrays. But that makes it fast, really, really fast, even if you have a very low number of observations, and all the time is going to interrupt between Python and Rust. Okay, I'll skip DMDT maps, which is cool, but still. And going to my last slide. So we have dozens of light curve features which run really, really fast, and you could parallelize them in multiple threads very fast, which not affected like multiprocessing or multi-threading things affected by GIL in Python. It's used by ZTF LSST alert buckets to analyze alerts real life of photometry coming from ZTF, and will be used to analyze LSST alerts in future. It is good covered by TESS. It has binary views for all popular and non-popular platforms, so you could pip install it right now. Thank you, and sorry that I used more time than I should. Thank you for your attention.
That's great, Konstantin. Thank you for sharing with us your package and also all your enthusiasm about Rust. I know there are some Rust users in the participants channel that I can see here. And so they might have some questions. At this point, we're going to open things up to any questions about either package. If you just use the raise your hand or drop it in the chat and I can read it out. Otherwise, maybe I'm going to get things off to a start. Rebekah, you talked about running things in the cloud. You mentioned Google Cloud, but you also mentioned something called Tyke, and I'm not familiar with that.
Yeah, Tyke is actually, maybe I can find it on mass. So it is, something that MAST is doing to try and
Okay, I'm not familiar with what MAST is either. So
okay, well then I'm gonna start from the beginning. Okay, so MAST stands for, and I'm gonna pronounce this wrong, so please forgive me. It is the Space Telescope Archive portal. So it's the Mikulski Archive. I'm gonna actually share my screen so you can see what I'm doing.
Yep,
that might be more beneficial. Okay, let's do share. Okay. All right. I'll put this down here. Okay. So MAST is this. It's the Mikulski Archive for Space Telescope. Is where all the TESS data gets stored. So you can go to the TESS portal. To the portal, and you can type in an object of interest. So Katie Airy, for example, and then that kind of basically shows you where it comes up with a list of all the data, whether it be on Swift or TESS. I click TESS, and it will find the data being just TESS for me. But they've also created this kind of Jupyter Hub area. So TIKE stands for the Time Series Integrated Knowledge Engine. And you have to have an account with Space Telescopes. It will be like sign in with MAST. And that will take you to essentially like almost like a Jupyter Notebook configuration workspace where you can create new notebooks. And then you can specifically choose the one that's tailored for lightkurve, and using lightkurve with things, and therefore you can like have it has lightkurve already inbuilt into it, and you can run it like you would run a Jupyter Notebook essentially. Right. And so some of the data is on Amazon Web Services, like actually on the cloud, and then the TIKE can also interact with that data as well, or it's another way of again using lightkurve but not installing the package on your computer. So,
yeah, great. Yeah, I hadn't seen that before. And Jupyter Hubs are very popular now, so it's nice to see that you're integrating it directly with your data.
Yeah.
And named after our after the former Congresswoman. Yep. Okay, we have a question from Joss. Do you want to unmute and say your question?
Sure, I can do that.
Yep.
So my question basically is from a very high level point of view, should we think of Rust as a memory safer replacement for C or C++ for performance sensitive binaries within our Python modules, or are there any kind of differences in how we would use that?
Yes, definitely. So the Rust is a great replacement for C++ or C or Cython or whatever you use to create a performant code for Python. Memory safety, really cool thing because it saves a lot of time and removes a lot of nasty bugs you could have and you could miss for a while, yes, and which could affect your scientific results because of undefined behavior. Also, you could use Rust if you would like to use some, for example, C code or code having C interface, but you need to add a bit upon of it, yes. So use it instead of Cython in this way, yes. So you bind some C library or Fortran or C++, something with a C interface, and you add a bit of code for NumPy, for parallelization, for something else you need, and you create a binary extension for Python you could use. So, and from other side, of course, Rust is not major for science, so there are not a lot of Rust packages you could use for science, yes. So it's basically for things you would like to write from scratch or for which you could easily get C or other type of bindings.
Great. Other questions for either Rebekah or Kostya? We have a hand up. Abdu, do you want to unmute? And
yeah, this is a question for Rebekah, and is how do you deal? How do you guys at the GOF deal with at the Guest Observer Facility deal with leading, or I don't understand what's the role of the Goth in lightkurve and being at NASA and dealing with NASA regulations and contributing to open source software and things like that, licenses and things like that. Can you say just a little bit about that stuff?
So we recently took over lightkurve. So it used to not be under us. We recently took over the working on the code itself. With regards to how that fits in with working at NASA, so I am actually a contractor. So I work through the cooperative agreement. So I work at UMBC, but I work at NASA through UMBC. With regards to software and lightkurve and things like that, I would have to say that's above my pay grade for specifically addressing that question. But you can send those types of questions to my boss, Christina Hedges, who is the director of the General Investigator Program at NASA Goddard, and she would be in a better position to answer those questions for you.
She was online for a while, but she might have left.
Yeah, she's not now.
Okay.
All right, thank you.
Thank you.
All right, and as I mentioned, I only recently learned Rust users are called Rustaceans. For those of you who are using Rust, why did you choose it, or why did you, and how did you learn it? Why did you pick that over, any of the other new languages like Julia and other things that are hot?
Well, it seems just from the slides Costa was showing that speed is definitely a factor. That
So maybe I'll ask, how did you learn it then?
Okay, yes. So so it's speed and safety, because I tried different things for C and C++ before, and just for new project, it wasn't historically it wasn't the way, where I had some Python code and I would like to speed it up. It would be a great idea to do it, but initially I had some very, very simple features, and I just couldn't make my Python code work fast with the database we used. So it was very slow to parse the database output, and it took much more time than calculating the features, and I couldn't parallelize it. And I was just interested to go for some new language. So before it, I tried Julia, which is great, but just doesn't fit my needs sometimes, because it has a huge runtime. You should install somehow to users' computers. And Rust is cool because it's a general purpose language. So it was, for example, super easy to create a web API for features, which we use in SNAD viewer and in other projects where we don't have opportunity to use Python, but we have opportunity to go through HTTP and to request these features.
And so I guess for those of us who are interested, is the online Rust tutorial in their docs, is that a good place to start? Is that?
Yeah, so Rust, official Rust book is a great thing to start with.
Great.
Definitely, yeah.
All right, I think we have time for one more question, if there are any lingering questions. While people think them up, I'll remind everyone that next month we're doing a joint meeting with the SciCodes group. Following that is going to be Grad Lightning Talks, and following that is going to be teaching computational astro. Any final questions?
Any final pets?
Any final pets? Yeah.
If you have an animal, this is your opportunity to show us.
Mine's snoring here. All right. If there's an advent of code problems, indeed, that's a great way to force yourself on a new language. All right. If not, let's thank both of our speakers again for wonderful talks. Thank you for taking the time to share with us today.
Thank you.
Thank you all very much.
Thank you, everybody.
Thank you.
And I'm going to end recording.